All right. So in this module, we're going to talk about what we call the thermodynamics of point defects. And so if you're not familiar with what thermodynamics is, that's fine. We'll talk a little bit about what that means. Okay. So we just finished in the previous module talking about these distortions. So we had point defects, either a vacancy that you can see here or an interstitial extra atom that you can see here. And we have tensile stress and compressive stress in these cases. And here's an actual image. It's a little fuzzy, but again, keep in mind this is an atomic level image of a particular structure, and you can actually see those types of vacancies here. And so these are real things that we can observe with very high-powered microscopes. So keeping in mind these things that we envision in a lattice, imperfections, and that they actually exist, what I want you to come up with is why. So what I want you to do is brainstorm some possible ideas why defects, so it doesn't have to just be the ones we talked about, but we talked about point defects. Why do you think these things would exist if there's this distortion that it introduces to the lattice, and therefore, you would assume a cost associated with that distortion? So brainstorm some ideas. This will be in the quiz, so you can pause this and go put in those ideas, and then come back and I'll talk to you some more about why these things actually happen. Okay, so let's take a look at these ideas. So hopefully you've come up with some interesting ideas of why this occurs. And if you've come through the curriculum, maybe if you're a chemical engineering student and you've had a few more classes than the others, you might have a better idea of why this is. But it all comes back to that term thermodynamics. And so when we talk about thermodynamics, and I'm going to give you the really hand wavy version of this, but there's a energy cost associated with a defect, right? Because a crystal wants to be in that perfect structure, anything that we do that is imperfect from that would require an energy cost. So one thing you can think about is the vacancy. If we have a vacancy, it means we, in essence, removed an atom from the lattice site, right? And that would require breaking all of those bonds with its nearest neighbors. And so we would have to put energy into that system, right? So you can think about it as the removal of an atom. All right, so that cost energy. Additionally, adding something extra, this badly distorts the lattice. And you can see it here. It's not just affecting that atom. It moves the atoms around it in multiple layers. You can see a distortion occur, and so that also requires energy for that to occur. So we can't just input an atom with no cost. That would require a lot of energy. So then it brings us back to the question of why this occurs. And that gets us to the second part. So we have an energy cost, but we also have disorder. We expect disorder at temperatures above, our absolute zero of 0K, right? So this is a concept that gets covered in thermodynamics, but just in general, when we're above 0K, there is thermal energy, right? And that thermal energy causes atoms to vibrate. And having a vacancy causes them to vibrate differently. And so that is the disorder in this lattice. Also, there's another type of disorder. So imagine we have two materials. So, one metal over here that's purple, one metal over here that's green. If those are placed next to each other, that's a highly ordered structure, right? But if we give it enough energy, we would want to try to, these laws, the thermodynamic laws, would tell us that they want to try to mix and reduce that orderedness and get disorder. And so you have this much more disordered, random solution that you see over here. And so this is known as mixing. And so this is also another form of disorder. And this all gets to something that you'll talk about more in depth in other materials classes or other engineering classes, if you take a thermodynamics class, is entropy. And so entropy is kind of our code for disorder, and disorder happens with increasing temperature. So let's take a look at that. And you've probably seen examples of this, and maybe you just don't know. So just think of the different phases of matter. We have a solid here where everything's very tightly bound and ordered. We have a liquid where it's a little bit looser and things are free to move about one another. And then you have a gas where there's no longer very many bonds between the atoms, and they're really free to move in a random Brownian fashion. So that is caused by an increase in temperature. So an increase in temperature causes more and more disorder, and therefore entropy with increasing temperature. And so this is an example of that. And so that's why we would expect in a given solid, if it's above 0K, we don't expect it to be a perfect crystal anymore, because there's increasing energy. Even if it's just a little bit of temperature at room temperature, for example, those that increase in temperature is driving more and more disorder until we break it apart and get a liquid. And so that's what drives the appearance of point defects, so vacancies, interstitials, and so forth. And so that's something that we can kind of formalize and put into more precise understanding of defects.